Hello, curious minds. Today we're embarking on a journey to understand one of the most fundamental forces shaping our world, and indeed, the entire cosmos: gravity. Specifically, we're going to delve into the fascinating story behind the gravity of Earth. It's the invisible hand that keeps our feet on the ground, prevents the oceans from floating away, and holds our atmosphere in place. Without it, life as we know it would be impossible. But how did we come to understand this pervasive force? For centuries, people observed its effects: objects falling, planets orbiting, without fully grasping the underlying principles. Early thinkers like the ancient Greeks pondered why things fell. Aristotle, for instance, believed that objects fell because they sought their natural place at the center of the Earth. Fast forward to the 16th and 17th centuries, and a revolutionary figure emerged: Galileo Galilei. Through ingenious experiments, he challenged Aristotelian physics. His most famous, though possibly apocryphal experiment, involved dropping objects of different masses from the Leaning Tower of Pisa. The remarkable finding: they hit the ground at roughly the same time, demonstrating that all objects accelerate towards Earth at the same rate, regardless of their mass, neglecting air resistance. This was a monumental shift in understanding. Meanwhile, astronomers like Johannes Kepler were meticulously charting the movements of planets. Kepler's laws of planetary motion described how planets orbited the Sun, but not why. The why would come from an intellectual giant of the 17th century: Sir Isaac Newton. The name is synonymous with gravity. The popular legend tells of an apple falling on his head, sparking the epiphany. While the specific anecdote might be embellished, the core idea is profound. Newton realized that the same force that pulled the apple to the ground was responsible for keeping the moon in orbit around the Earth, and the planets around the Sun. He understood that gravity wasn't just a terrestrial phenomenon, but a universal one. Every particle of matter in the universe attracts every other particle with a force directly proportional to the product of their masses, and inversely proportional to the square of the distance between their centers. This became known as Newton's Law of Universal Gravitation. It was a single, elegant equation that explained everything from falling apples to the majestic dance of galaxies. This was a paradigm shift, unifying celestial and terrestrial mechanics under one grand theory. Newton's theory was incredibly successful, allowing scientists to predict the movements of planets with remarkable accuracy, and even leading to the discovery of new planets, like Neptune, through gravitational perturbations. So what exactly is the gravity of Earth? It's the attractive force exerted by the Earth's massive body on any object near it. This force is what gives objects weight and pulls them towards the planet's center. The Earth's gravity is primarily due to its immense mass. While the force of gravity between two objects depends on their individual masses, the Earth's sheer size makes its gravitational pull dominant in our vicinity. The strength of Earth's gravity isn't perfectly uniform across the globe. It varies slightly depending on factors like altitude, local geology, and the Earth's rotation. For example, gravity is slightly weaker at higher altitudes because you're further from the Earth's center. This is why astronauts in the International Space Station experience what we call microgravity. Even though they are still very much under Earth's gravitational influence, they are constantly falling around the Earth. The escape velocity from Earth, the speed required to break free from its gravitational pull, is approximately 11.2 kilometers per second, or about 25,000 miles per hour. This is the incredible speed rockets must achieve to send spacecraft into deep space. The Earth's rotation also plays a subtle role. Because the Earth spins, the centrifugal force is strongest at the equator, slightly counteracting gravity. This means you would weigh infinitesimally less at the equator than at the poles. For over 2 centuries, Newton's theory reigned supreme. Then, in the early 20th century, a new revolutionary theory emerged from the mind of Albert Einstein: the theory of general relativity. Einstein proposed a radical new way of looking at gravity. Instead of a force, he described gravity as a curvature of spacetime caused by the presence of mass and energy. Massive objects like Earth literally warp the fabric of spacetime around them. Objects, instead of being pulled by a force, simply follow the curves in this warped spacetime. Think of a bowling ball placed on a stretched rubber sheet. It creates a dip. A marble rolling nearby will curve towards the bowling ball, not because it's being pulled, but because the sheet itself is curved. General relativity has made incredibly accurate predictions, including the bending of light by massive objects and the existence of gravitational waves. It's even crucial for technologies we use every day, like GPS. GPS satellites need to account for both special and general relativity, as gravity subtly affects the passage of time. Without these relativistic corrections, GPS systems would quickly become inaccurate. So, while Einstein's theory provides a more profound and accurate description of gravity, for most everyday purposes, Newton's laws still provide an excellent approximation. The apple still falls just as Newton predicted. Earth's gravity isn't just about keeping us grounded. It has profound effects on our planet, including the tides. The gravitational pull of the moon and, to a lesser extent, the sun, creates bulges of water on opposite sides of the Earth, leading to high and low tides. Deeper within the Earth, gravity plays a crucial role in geological processes. The immense pressure exerted by the Earth's own gravity contributes to the heat in its core and influences the movement of tectonic plates. Earth's gravity also acts as a shield, pulling in many incoming meteoroids, causing them to burn up in the atmosphere before they can strike the surface. This protects us from countless extraterrestrial impacts. The study of Earth's gravity continues today. Scientists use incredibly precise instruments like gravimeters to measure tiny variations in the gravitational field. These measurements help us understand everything from subsurface geology to climate change effects on ice sheets. These gravitational anomalies can reveal hidden structures beneath the Earth's surface, helping in the exploration for resources and in understanding geological hazards. As humanity ventures further into space, a deeper understanding of gravity, both Earth's and that of other celestial bodies, becomes increasingly vital. From designing spacecraft to establishing extraterrestrial colonies, gravity is a constant consideration. The story of Earth's gravity is a testament to human curiosity and our relentless pursuit of understanding the universe. From falling apples to warping spacetime, our journey to comprehend this fundamental force has unveiled some of the most profound secrets of nature. It's an invisible hand, constantly at work, shaping our world and guiding our exploration of the cosmos. Thanks for joining us on this fascinating journey.